mechanics, you have something called linear superposition principle, and what it means is that if you have a two possible state of a quantum system, like say spin up or spin down of a spin up particle, it can be electron, it can be proton or neutron, anything you can think of. We know that if an electron can remain in up and down state, it can also remain in a linear superposition of up and down. Okay, so because you have the so-called the Hilbert space formalism for quantum system, and that allows this superposition principle, which means any two vector, if you superpose linearly, there is also an admissible vector in that Hilbert space. That means quantum system is supposed to remain also in that kind of superposition state. Okay, so once you have this, what happens is you say my spin up is 0 and spin down is 1, but then you have also like alpha up plus beta down, or a up plus b down, where a and b are complex numbers. That means you have a physical state which is alpha up plus beta down, or a up plus b down, but that physical state gets translated to a logical state which is alpha 0 plus beta 1. Okay, so this logical state is completely distinct from classical way of storing information. Okay, because this logical state is neither 0 nor 1, it is both 0 and 1. So that allows you to have a new way of storing information in quantum state. That is essentially what I just described, is essentially the notion of quantum bit, okay, or qubit. You might have heard from Professor Aditi Sen's talk yesterday, or maybe today's talk also. So what is the big goal in this area? The big goal in quantum information theory or quantum information science is to exploit principles of quantum theory for various information processing tasks which are otherwise impossible. Okay. So we all know that quantum theory has been one of the most remarkable theory over the last 100 years or so, and till now there has not been a single prediction of quantum mechanics or quantum theory which has not been tested in experiment. So this is quite amazing. I mean, you have a theory which has been tested to its highest precision. Okay, so how does the theory was built? The two pillars of quantum theory, one is linearity and other is unitarity. These are two pillars on which this quantum theory is actually based. That means any prediction that you try to make using linearity or unitarity, you have to respect that. So let us see what are the predictions of this linearity and unitarity. So before that, let me try to spend a few minutes about trying to explain in more detail about this qubit. So as I said that you identify any two distinct set of a quantum system like spin up particle, like you say, okay, it is up state, it is 0, if it down, it is 1. But then by linear superposition, you have a state which looks like something like this. That means an arbitrary state of a two-state quantum system is actually your quantum bit, or in short, you say it is a qubit. So the main difference that you see now is a classical bit can remain either 0 or in 1, but a qubit can remain simultaneously in 0 and 1. And this inherent parallelism is often has been cited as something responsible for new type of computation, that what you call as quantum computation. And this kind of computation you don't see in classical world. This was the first realization by David Dice, and that is the reason we regard him as the father of quantum computer. Okay. So let me try to explain a little more about this quantum bit, or the so-called this qubit. So as you see here, you can write your qubit mathematically like this, like alpha up plus beta down, which is nothing but alpha 0 plus beta 1. Okay. Now these complex numbers alpha and beta could be known or could be unknown. So if you don't know these alpha and beta, then you will say that this state is unknown to you. Okay. So what I mean is the following: that suppose I start with a fiducial state like this, zero state, and yes, somebody is saying something. Hello.
No, sir.
So suppose you start with this fiducial state 0 and you apply some unitary and you create a state alpha 0 plus beta 1. Okay, so when I say you apply unitary, what it means is physically you can think of that your spin, like say electron spin, is pointing along z direction. Okay, then you switch on your magnetic field along, you know, having component along say x, y, and z. Okay, so that will induce essentially a rotation, okay, which will be causing a evolution of the state from this to this state. Okay, so essentially this alpha and beta will depend on the orientation of the field direction, like along which direction, like theta and phi, and this if you use the polar coordinate, uh, you will have the theta and phi dependence. And essentially, alpha is nothing but cos theta by 2, and beta is your sin theta by 2 times exponential I times phi. Okay. So what I want to say here is that if you know in which direction you have applied your field, you know essentially what is alpha and what is beta. Okay. So in other words, if I know what kind of unitary I have applied to this state and I have created this state, I know essentially what is alpha, what is beta, and in that case, the state of the qubit will be known to you. But suppose you have prepared the state and you give it to me, okay? I don't know along which direction you have applied the field. That means I don't know what is theta, what is phi, okay? So that means I don't know what is alpha and beta. So that is the thing that I am trying to highlight here, that if I don't know these complex numbers, then the state of the qubit is in an unknown state, okay? The next important statement is the following, that given a quantum bit or qubit in an unknown state, it is impossible for you to determine the state. Why? Why it is so? Because to determine the state, what you have to do is you have to find the average of at least two non-commuting observables, in this case like sigma x, sigma z, or sigma y and sigma z. Okay, so you have to find the average of these observables in this state. That means, as you know, to determine the average, you should have an infinite number of collection of identical particles. That means you should be having a collection of large number of quantum states like qubit in the same state, and then from that you would perform the measurement, which is technically sometimes called also quantum state tomography, but that is a different story. So essentially, just try to understand that to determine the state, you have to do measurement of some physical observable, and you actually have to measure the average of the physical observable, and that will amount to the requirement that to do that is essentially you should have an infinite number of copies. So that is the reason that given a single quantum bit in an unknown state, you will not be able to determine what is alpha and what is beta. Okay, and this has a profound consequence in quantum information, as you will see later on. Uh, so now, if you ask the following question, that how many bits do you need to specify a quantum bit? Okay, the answer is we need infinite amount of bits, because to specify two real numbers in bits with infinite precision, you need infinite amount of bits. But quite, I mean, contrary to so many bits you need to specify this quantum bit, how many bits you can extract? You can extract only one bit. Why? Because if you have a quantum bit like this, and if you do a measurement on this quantum bit, you will get either 0 or 1. So that will give only two possible outcome, and log base 2 times number of measurement, number of outcome, essentially log base 2 which is essentially 1. So that will give only one classical bit. So even though it has a large amount of information, we can extract only one bit by measurement. So most of the information that is contained in this quantum bit, which is not known to you, is actually inaccessible to you. Okay. So these are the important things that you should try to understand. Actually. So the next concept is something called quantum entanglement, which already you may be familiar a little bit. And this was first time coined by Schrodinger, again one of the founding father of quantum mechanics, in 1935. So at that time, he could actually realize the importance of this entanglement, because this is his statement. He said that I would not call entanglement one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So you see, this is a very profound statement at that time, because the theory was, developing at that time from 1926 and onward. And just after 30 years, after 10 years, in 1935, he introduced this concept, and he could really, uh, appreciate the deep meaning of this quantum entanglement. Okay, so in quantum information, essentially we are trying to use this superposition and entanglement, and also a few other non-classical features, and trying to do something which is not possible with classical information science. So what are those things? Essentially, you have the quantum computing or quantum computation, quantum information protocols, quantum cryptography, and there are many other technology that has emerged over the last several years. So I have not listed here, but it has a lot more. I mean, the area has really diversified over the last 30 years. So in quantum computation, what you have essentially, you have trying to explore some algorithm which will be much more faster or much more efficient compared to classical algorithms. We have the computational complexity, decoherence, error correction, experimental implementation, and in this you have teleportation, dense coding, remote state computation, remote control, and in this setting you have so-called DB84 scheme, entanglement scheme, secret sharing, and many more things. Okay, so again, as I keep emphasizing, you have this quantum superposition or quantum coherence, entanglement, quantum correlation, and non-locality. These are the things that you want to utilize and see how do these features benefit in implementing all these tasks. So next I try to answer this question. Uh, so just give me 1 minute. There is some phone coming. हेलो हाँ 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 ठीक है हाँ हाँ okay, so the main title that I flashed in my my beginning of my talk is what is quantum information. So you may be surprised to know that this is not yet defined in a more fundamental way. Okay, so this is not just my feeling or my statement, but also this is a view that has been quite clearly expressed also by Richard Josa in 2004, who says that quantum information theory has developed into a vigorous field of research despite the fact that quantum information as a precise concept is undefined. Indeed, the very idea of viewing quantum states as carriers of some kind of information, albeit unknowable in classical terms, lead naturally to interesting questions that might otherwise never have been asked and corresponding new insights. So this is a very, very profound statement he has actually made, that even though we have been working in this area for last 30 years, and several people are really working in this area, and not only that, we have made so much progress on theoretical side as well as on experimental side, but still we do not yet have a definition of what is quantum information. Okay, so so what I will try to do, during this talk is I will try to give one of the possible definition of what is quantum information. Okay, so so when you have a quantum system and you store some information in that quantum system that carries both classical and quantum information. Okay, when you think of a quantum bit, it has both classical as well as quantum information in the quantum state. Okay, so quantum state contains potentially a vast amount of information, which I explained a little before. Because to specify a qubit, you need infinite number of classical bits, and those vast amount of information is actually inaccessible to an external observer. Because if somebody has prepared the quantum state or qubit, and that qubit is given to me, I don't know what is alpha and what is beta. Okay, so to me, it appears that this inaccessible information is, in some sense, is quantum information. Okay, but that is not still enough, because I should be able to characterize, in a more, more precise way or more refined way, what this actually is, how this is different from classical information. Okay, so that is the one of the goal, main goal that I will try to convey to you, that by trying to figure out the various uh, you know uh, features or properties of this quantum information, and how do they differ from classical information, by answering those kind of questions, maybe we will be able to make some progress in trying to define what is quantum information. Okay, so the amount of information that we can extract from a quantum state via measurement is something you can say accessible information, and this is classical information. And quantum information differs fundamentally from classical information in many ways. So it is therefore important to know those differences, and in the end, that may provide a tentative definition of what is quantum information. So these fundamental differences between classical and quantum information can tell us what is actually quantum about quantum information. Okay, what is that key thing? Okay, that puts demarcation, between classical and quantum information. Okay, so let me go to answering that question. That is, what are the differences that you see in these two kind of information? Okay, so these understanding these differences, are of fundamental and practical importance. Because why this is fundamental? Because they can shed new light on the boundaries between classical and quantum information, and also it has practical application, because you can exploit the limitations or the differences for various security purposes in quantum computer and quantum communication. Uh, so what are the no things that you have figured out? I mean, people have figured out. First thing is something called no cloning of quantum information. Second is no deleting, that is you cannot delete. You cannot design NOT gate for unknown qubit. You cannot also design Hadamard gate for unknown qubit. You cannot design CNOT gate for two unknown qubit. You cannot do partial erasure. You cannot hide information. You cannot also mask. There is masking of quantum information. And there are a few more things which I have not listed, but I will not go into detail of all these, but I will try to highlight some of the things here. Okay, so no cloning theorem tells you the following, that the most familiar operation that you do in classical computer, that is in your desktop or even in your laptop, is all the time you copy file from here to there or here to your mobile or here to pen drive and so on. Okay, that means classical bit can be copied freely. Okay, given 0 0, you can transform to 0 0. Given 1 0, you can also make it to 1 1. Okay, that means this is the input, this is the blank state. You are able to make two copy. This is input, this is blank. You can make two copy. But if you have a quantum bit, can you do the same thing? Okay, that is, you have a psi here as input, and you have a blank state here, and this is a machine, and you send the input and blank to the machine, and then in the end you want to get these two. Okay. If you can design such a machine, then you will say, okay, I am able to make copy of this input state. Okay, but quantum theory actually rules out this option. Okay, and this simply follows from linearity and unitarity that tells you that it is impossible for you to make a copy of a quantum bit. But nevertheless, you can, if you know a quantum bit, a quantum state, you can clone perfectly. Also, you can copy your quantum bit if they are already in orthogonal state, like follows from one. Okay. Linearity. And why this is so? Because if your quantum bit is in state 0 or 1, they essentially carry classical information, and you know you can copy classical information. If it's not the case, then you will not be able to do this also. Okay. So to be consistent with the classical information, I mean the possibility of making copies of classical information, this is also possible. Okay. So 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 what the theorem telling? It tells you that there is no linear map that can transform psi 0, and this is some state of the machine that you can think of. This is the initial state of the machine, which will transform to psi si and si for any arbitrary state. Okay. So if you want, I can prove this, but so Aninder, should I do the proof here? Hello? But but I think that will take too much time. Already 5 o'clock. I think I should skip that. Yeah. Yeah. I was planning to use slide and iPad, but I think now there's not much time. So okay, so let me go to the next thing, which probably you can understand. That is no cloning from just from unitarity. Okay. So this theorem is about impossibility of making copy of an arbitrary qubit using just linearity. But there is another proof that was given by UN. This was by Wouters and Jurek, and this is by UN. Just I think 4 years after that paper. So that tells the following: that there is no unitary transformation that can clone two non-orthogonal state like this. That is, you have the input and you have blank state. You make two copy. You have another input psi 2 and a blank state. You make it psi 2 and psi 2. Okay. I think there is some typo, some extra letter appeared here. So if you can do this by unitarity, then you know whether this is possible or not possible. Because if this had to be unitary, then this must reject the overlap. That means this times this should be equal to this times this. Okay, because we know that if we map a vector by unitary transformation, any two vector overlap should be preserved. Okay, if the mapping is unitary. That means on the left hand side we have psi 1, psi 2. On this side we have psi 1 times psi 2, and again psi 1 times psi 2. If you take modulus of both sides, you get psi 1, psi 2 modulus is same as this square, I think square has gone up a little bit. This side there is a square actually, and this can never be satisfied. Okay, cannot be cloned by unitary. Null this is zero. In this side also zero, so there is no contradiction. So that is consistent with what you know. Four. Okay. So yeah, so this came in 2004. That is stronger no cloning. So what is the aim here? The aim is the following: that we know now that you can always copy classical information, but you can never copy quantum information. Okay, that is classical bit can be copied, quantum bit cannot be copied. Okay, so the next question is what prohibits me in doing this? Okay, is there anything we are missing that we are not able to make a copy of single copy of a quantum bit that classically you don't need anything extra, okay? Because whatever is input, you can always make a copy. You don't need anything extra. So, so what he asking is following that in addition to the input and blank, is there any extra information that I should send to the machine so that it can create two copies? The answer is surprisingly that in quantum case, to produce an extra copy, one must supply the full information. No less, no more. You have to supply the exact information that you want to make a copy. That means, basically, what he's trying to tell you is that you have to recreate the copy itself, okay, without taking the help of the input, but you cannot make copy. So, see, so the precise statement is the following that any physical operation taking this psi I and a I mathematical statement, and that is so. This proof is simple. So I will give the proof here. Actually, this is two-line proof. So in quantum, but in command system, you hold literally, and then you press out. Okay, if you press out, you will get this so-called this completely positive mirror. So the what Can you hear me? No, 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 no. No. Now I'm not speaking, but I'm waiting to hear from you. Is it clear, or should I continue? Hello, hello. Okay. So if you don't listen, if you're not able to hear, you tell me, and maybe I will again try to reconnect. So what I'm trying to say is that the proof of this is actually simple. So I will try to give the proof here. So one part is actually trivial. So if there is the operation taking this to this, then you already this can happen. Okay, but the opposite is little a little extra argument involved. So assume that you can have this by including addition. You can realize any CP map as a unitary evolution in a enlarged Hilbert space, as I said. And then in this you will have that is unitary, then this will satisfy. That is, this matrix element should be equal to this matrix element. That if you use this lemma, it tells you that two sets have interconnected psi I from AI alone just by get this. Okay, that is the proof. Uh, so next, I want. Are you able to see? Hello. A bit. Oh. Uh, so I think there is still some issue with internet. I think so. Uh, so can you hear? Can you hear now? Or should I use my headphone? Will that be clear? I don't know. So uh, let me try to use my headphone. Let me use my headphone. I don't know if that will be better. Uh, so tell me if it is slightly better. Can you? Is it better now? Hello. Better? Okay. Okay. Maybe I should use this. Okay. So what I initially you have input 0 and you reset to 0 and you have input 1 and you reset to 0. Okay. And we have to generate this much amount of entropy. Okay, and this has implications in reversible computation, resolution of Maxwell Demon, and so on. And also that is one of the reason that uh, that led Landau to think that information is ultimately physical, because to store process information you need physical system, and that actually motivated many people to to connect physics and information. And actually that has also a deep impact on the field of quantum computing also. Now, Uh-huh. Is it okay now? Is it okay? Okay. Now, if you want to erase a quantum bit, that is also possible. That is, given any input, you reset to 0, and that you cannot do by reversible operation. That is, you cannot do by unitary transformation, but you can do by irreversible operation. Okay. And the proof is again simple. Why you can't do eraser by reversible operation? Because in quantum theory, you know that any reversible operation is just essentially unitary transformation. So process of erasure takes psi to 0. So suppose you have two non-orthogonal qubit like psi and phi, and to want to erase, that is, you want to take psi to 0, then you have to the overlap, that is psi phi should be equal to 0 0, but 0 times 0 is 1, and psi phi, this means psi times phi is 1. But this is a contradiction because this is two are non-orthogonal. Okay, that is the main reason that you cannot erase quantum bit by reversible operation. Okay, but if these are two orthogonal, 0 and 1, then also you see that you have a contradiction. Okay, so this shows in a very simple and profound way that neither classical information nor quantum information can be erased by reversible operation. Okay, because here this could be arbitrary quantum bit, but here quantum bit in orthogonal state like 0 and 1, but then they carry classical information, but still you get a contradiction. Okay, because this side is 0, but this side is 1. Okay. Next, I come to this non-deleting, which is the following, that classically you can always delete from two identical bits, like 0 0 can go to 0 0, and 1 1 can go to 1 0. But can you do same thing for quantum bit? That is, given two identical quantum bit like psi psi, I want to reset, I want to delete one copy and keep the other intact by jointly acting on this psi psi. Okay. Though typically what I have in mind is like this: I have psi psi, and I have some machine here, and I want to create psi and then sigma here. Okay. So again, you can show, and that is essentially your non-deleting theorem. So this is more precise statement. There is no quantum mechanical transformation which will transform this to this, and A prime are initial and final state of the ancilla. And if you demand that final state of the ancilla is independent, then there is no way to delete the information. But if you allow this, then what can happen is you can swap the information to the final state of the ancilla, and it will be remaining there. That means you can actually try to recover the information from the final state of the ancilla. So if you don't want that your information should be hidden anywhere in the deleting machine or any other part of the universe, and if you allow swapping and tracing, then the result will reduce to erasure, and extract copy will not play any role in a deleting mechanism. So that is the main reason that why you say that it is impossible to delete in a closed system. Okay, because this transformation can be unitary also. Uh, so this no-deletion and stronger no-cloning taken together actually gives some kind of permanence to quantum information. What it means is the following, that uh, that the no-deletion tells that given any two input and machine state, there is no way to do this. That is, it is impossible to eliminate quantum information. And why this is impossible? Because quantum theory only tells you that if you do this by some means, this will be simply sitting somewhere here. Okay, then that means the only option is to move information to the ancilla part where this will continue to exist, and second copy can always be resurrected from the final state of the ancilla. So what this is trying to tell is that stronger no cloning tells you that to make a copy you have to provide full information. To delete a copy, you have to move the full information from here and keep it here. That means you can only move your information from here to here, or here, there to here, but you can never be able to create or destroy information. So that is the thing, that no deletion and a stronger no cloning, they have a common feature, that in cloning the first copy provides no assistance in making the copy second copy. In deleting also, first copy provides copy provides no assistance. So considering non-deleting and stronger non-cloning together, they imply that quantum information has a quality of permanence. And this quality you don't see in classical world, okay? So to put it in other words, to create a copy, we have to import information from some part of the world where it already existed, and to destroy or to delete it, we have to export quantum information to some part of the world where it must continue to exist. That is, to create it, you have to bring it from somewhere, and to delete it, you take it from here and keep it somewhere. Okay, that is the only option you have. So uh, also a lot of work has been done. So I will highlight one of the work done by our group long back in 2005, Aditi and Ujjwal, along with Paradex group. So they have proved that these two non-deleting, the two theorems like non-deleting and no-cloning, actually you can derive from basic law of quantum information. That is, in a closed system, quantum information, actually one can derive these two theorems. Okay, so in some sense, these two theorems are actually connected to conservation of quantum information. And also they have shown that there exists intimate connection between non-deleting and no-cloning, and also the second law of thermodynamics. So I will not go into detail because that will involve a little more elaboration. So, but if you're interested, you can look at this paper. Uh, so again, I will not go into detail. So I will just highlight here that in addition to no cloning and no deleting, there is something called impossibility of universal NOT gate. And why that is impossible? So that is, we know that given a NOT gate, we can always flip 0 to 1 and 1 to 0. That is essentially done by, you're not getting classical information processing devices. Similarly, if you want to store quantum, if you want to deal with quantum bit, like in this 0 and 1, you can transform 0 to 1 and 1 to 0, and this is essentially your sigma x. So apply sigma x, the Pauli matrix, then you can flip it to 0 to 1 and 1 to 0. Okay. Now the question is, can you flip an unknown state like this? Can you do this? The why it is, because we know that to flip and cube it, we need an anti-unitary operation. That is, to transform psi to psi orthogonal, we need c times minus I sigma y, where c is conjugation. That is defined like this: c acting on psi will conjugate essentially these complex numbers, and sigma y is essentially a Pauli matrix along y direction, and this is anti-unitary. And the anti-unitary operation cannot be implemented physically because that is not a physically, not a completely positive map. Okay, so this was discovered by Bujek, Hillary, and Werner in 1999, and also realized also one of paper in same time. And all there is another difference. This is not really difference between classical and quantum, but this is a kind of difference between quantum bit in orthogonal state and in arbitrary state. Okay, that is, if you have your quantum bit in state 0 or 1, we know that if you apply Hadamard gate, we can create a superposition of 0 and 1, like this 0 plus 1 and 0 minus 1. This is well known, and this is quite useful gate because most of the quantum algorithm, they do use this such a transformation for arbitrary basis state. Is it possible? That is, suppose I give you an arbitrary qubit psi. I want to create psi plus psi orthogonal and up to 1 over square root 2. Similarly, I want to create psi to psi minus psi orthogonal. And again, you can show that this is not possible. But interestingly, you can prove that if this qubit has real amplitude, that is your alpha and beta are real, then you can design such a gate which will do this kind of transformation. So this brings out a difference between an unknown qubit and unknown real bit. Similarly, you can ask the following question: that can you design a C0 gate for a arbitrary qubit? C0 gate, we know what it does. Essentially, it does 0 to 0. I mean, it takes 0 to 0 0, 0 1 to 0 1. But 1 0 will change to 1 1, and 1 1 will change to 1 0. Essentially, what you're doing is it is doing nothing if first one is 0, and it will flip the second qubit if and only if this is, I mean, this is 1. Okay, so that is why this is called control NOT gate. Control upon this qubit, this gets flipped. You apply NOT if this is 1. Okay, so a control NOT for unknown qubit would look like something like this. So psi psi will go to psi psi, and psi orthogonal will go to psi psi orthogonal. You do nothing if it is instead psi, but you flip it if it is psi orthogonal. Okay, and again you can show that this is not possible. So what are the implications? Let 523. So implications are the following: that this NOT gate, Hadamard gate, and C0 gate are impossible for unknown qubit would mean that your quantum computer at some level are actually personal computer. Okay, because what can happen is, if you have a quantum computer, you are doing something, you are running some algorithm, then some other person like Bob cannot come halfway and start using Alice's quantum computer, because Bob cannot apply the required logic gate, as the initial state of the quantum computer will not be in the canonical computational state, because this is one of the requirement. When you want to run your quantum computing algorithm on a quantum computer, you reset, I mean, all your qubit in computational state like 0 0 0. Okay, then you apply Hadamard, then you do something and so on. Okay, but if if Bob doesn't know in which state the qubits are, he cannot apply arbitrarily this kind of logic gates. But classically there is no limitations on this basic operation. So quantum, I mean, that is the one main reason I say that fundamental laws of quantum theory says that any quantum computer will be strictly a personal quantum computer. And this is probably one of the reason many people may not know. I think this is one of the reasons that why you are not able to use. I mean, why everyone is not able to use IBM quantum computer? I mean, IBM online platform at the same time. You have to request and you have to get a window. You see, I mean, classically there is no limitation. Anyone can have access to any server, But once you have a quantum computer, you have to. I mean, only one person can use at a given time. It is kind of personal computer for him at that point of time. Okay, so you have to wait and you have to finish that task, and then somebody else can come and then start using that computer. Okay, so this is the implication that even if you design quantum computer, you have to wait for your time window to run your algorithm. Okay, I think this I will skip. I think there's not much time. Okay, let me come to this something called no hiding, and I will also try to tell you about no masking. So the question that I want to address here is something to do with loss of information. Okay, essentially, I mean, this has been one of the pressing questions over the last several decades. That if you have a quantum system and if it interacts with the environment, we know that it undergoes decoherence and system loses its purity. Okay, so your pure state psi will interact with something additional system, say A, and you can write down this kind of transformation. This is called Krauss operator formalism, which I don't know if you know, but maybe somebody will cover in this during this webinar. This is essentially how you describe an open quantum system dynamics. So if you trace out this part, then you will notice that your pure state psi psi will go to a mixed state state, but the mixed state essentially sum over ei psi projector times ei dagger. Okay. But if you are not familiar, don't worry. Try to. I will try to convey the main essence. So, so the main essence I want to tell here is that whenever a system is interacting with something additional system, it will lose its purity. So if you psi was a pure state, but in the end, it has become a mixed state. Okay, and it might happen that this decoherence process can lead to complete loss of information. That is, that is, what can happen is this final row that you obtain here could be completely independent of the input psi. Okay, so if that is the case, you will call as bleaching of information. That is, whatever information was there here is completely bleached out. Okay. So if that happens, then you will say that the physical process has led to loss of information. Okay. So that is the question I want to address here. So if there is a process that changes psi to some row, and this row is independent of the input, then the question that I want to address is, where is this missing information? Okay. So information is not here, but where that has gone. Okay. So there are many examples you can actually cite, starting from state randomization and quantum teleportation, thermalization, black hole evaporation, and many processes actually end up in this kind of scenario. Okay. So for example, if you have state randomizing process, whatever is your input, suppose your input is a quantum bit. If you want to randomize, your psi will go to I by 2, identity by 2. Okay. So that is something called randomizing operation. Okay. And also in thermalization, what happens? You start with input, pure state, you bring a heat bath, you allow them to interact, and in the end, you will see that this pure state will thermalize and reach a particular thermal state, which was in a definite, in a particular temperature state. Okay. So the big question is the following: that where is the original information had gone? Is it hiding somewhere? If it is hiding, where it is hiding? Okay. So this I will skip maybe because not much time now. So already 5:30. Okay. So the no hiding theorem, which is the theorem that trying to answer that question, is the following: that this no hiding theorem tells you the following. So classically, okay, so before telling the answer, let me tell you the following: that if you want to hide classical information, then there are two ways to do that. Okay, we can hide classical information in the correlation between pair of system, or you can move into another location. Okay, so okay, maybe a simplest scenario is something like this. So suppose I have some file, I have some secret file in my computer. I want to hide it from you. Okay. So what are the options? There are only two options. Okay. So either I encrypt my file, okay, and I keep it in my laptop so that you will not be able to decrypt or decode it, or I take my laptop from my office and keep it, in some locker in my home, or I take it to some other place. Okay. So there are only two options to hide classical information. Okay. But the question that I want to ask here is: can you hide quantum information in the same way? So if you could encode a quantum state into correlation between two subsystems, such that subsystem has no information, then you can say that you can keep the information in the correlation. So no hiding is trying to tell the following, that if this is missing, I mean whatever original was there, if that is missing, then that must move to somewhere else and it cannot be hidden in the correlation. So pictorially, I mean this is easy to understand. You have a system and it was in some definite pure state psi, and this is your big universe, and this start interacting with this, and then in the end the psi becomes rho, and whatever was there inside the psi, that has been completely washed out. So there's nothing here now. Okay. Now the no hiding theorem tells that whatever was here simply sitting in some part of the universe, okay, from which you can actually recover. That means, strictly speaking, there is no information loss. Okay. So this is the precise statement that let this input it get mapped to bigger state psi, where this psi, when I say this psi, this is the state of this whole thing. Okay. With the condition that uh, the reduced state of this big psi, which I denote as sigma, is fixed for all rho. Okay. If that is the case, then you can prove that the big psi in bigger Hilbert space will look like something like this. That is, whatever this psi was there at this port, input port, is simply sitting in some part of the ancilla. Okay. So that is statement that missing information is wholly encoded in the remainder of the Hilbert space with no information stored in the correlation between the two subsystems. As you can see from here, it is simply sitting here, and it is not getting entangled with this or between this and these two. Okay. So it is simply sitting ideally here. Okay. I think I will skip this. So again, this proof follows from linearity and unitarity. And one example, as I said, that you can think of a process where psi goes to I/2, and this is, as I said, this is something called randomization process. And if you imagine a unitary version of the randomizing process, that is input and ancilla, and apply unitary, which is something like this, then you can show that if you trace out this, you do get I/2. But then you can show that by no hiding theorem, as you have claimed, by doing only local unitary on the ancilla Hilbert space, you can get back this psi. So as you see from here, by doing only operation on this ancilla qubit 2 and 3, you can get this psi. Okay. So this has been also tested in experiment using NMR. So again, I think I will skip this. So essentially, they have the input, which is a coherent oscillation of this, in 0, 1 basis state, and then this is ancilla, and finally, this information is completely washed out from here, and you find in the third qubit. So finally, I come to no masking. The statement is the following, that what we want to, what we want to do here is the following, that we want to encode quantum information like a qubit in bipartite quantum state, which is an entangled state, with the condition that individual systems, they have no information about the input state. Okay. So suppose my input is psi, which is alpha 0 plus beta 1, and I want to encode that in a bigger entangled state, it's a big psi. Okay. And if I trace out one side, I should not see any dependence of that state. Similarly, if I trace out the other side, I should not see any dependence of the state on the input state. Okay. So that is the statement here. Can quantum information be hidden from both the subsystem and remain only in the correlation? If you could do this, then this may allow quantum information to spread over the spooky correlation and remain invisible to both the subsystems that are possessed by the local observers. That means you have Alice and Bob, and Alice encodes the input into a bipartite entangled state, and it is distributed between Alice and Bob. And with the condition that Alice has no knowledge about, Alice has no information Bob also has no information, but somehow if they come together, that is there in the correlation. Okay. So this process of spreading of quantum information over the quantum correlation, like quantum entanglement, we call as masking of quantum information. So the no masking theorem is trying to tell that such a task is not possible again. Okay. So what I stated in physical, I mean in words, is actually can be stated mathematically like this. So any operation is said to mask quantum information contained in the state of states A k by mapping them into some psi k, big psi k, in this joint Hilbert space, such that all the marginal of the state psi AB, I mean psi k AB are identical. That is, if you trace out B, you get rho A. If you trace out B, sorry A, you get rho B, and rho A and rho B, they have no information about the value of k. Okay. So you can prove that again by using unitarity and linearity. You can prove that an arbitrary quantum state cannot be masked. The proof is little bit involved, so I will not go into detail. So the sketch of the proof is something like this. We assume that you can mask two orthogonal states like S0 and S1 by encoding into psi 0 psi 1, and psi 0 psi 1 are shared by two parties like Alice and Bob. And then you try to see whether you can mask such a superposition state like mu S0 and mu S1 with arbitrary coefficient satisfying this normalization condition. And what you will realize that for arbitrary mu and nu, you cannot satisfy this requirement. Okay, so that is the essential idea. Did I give the? Sorry, I forgot to give the reference here. But this is the paper with Kavan Modi, also with Aditi Sen and Sende and Ujjwal Sen in 2018. So over last 2 years, a lot of other people have tried to work out, but again they have tried to prove that. So our theorem is true for bipartite state, but if you go to multi-party, then you can have a design, you can have a scheme where it can be you can actually mask quantum information. And recently, people have tried to do also deterministic and probabilistic masking. He tells that if you choose your quantum state secretly from the set like this, they can be deterministically masked by unitary operation if and only if they are mutually orthogonal, and also by probabilistic means if they are linearly independent. Okay, so by far, what we know about quantum information, we really don't know what it is. So what we have is actually an elephant, and we're trying to describe part of this elephant. So this I call quantum information elephant. So by trying to answer these kind of questions, that what is possible, what is not possible, what you can do, what we cannot do, we're trying to figure out various things about or various properties of this quantum information and trying to set what kind of rules they obey, or what kind of guidelines they obey, or what are the boundaries they respect, and so on. Okay, so this is the thing that I wanted to convey, and this is your psi. And typically, whenever we deal with quantum information, we take that synonymous with this psi. But if you, as I said in the beginning, if you want a precise definition, as raised by Richard Josa, we still don't have a precise definition. We understand we have made enormous progress over the last 30 years, but we don't have a definition. I will try to give a definition. Let us see. So before that, I will try to summarize. So what I try to tell you is that there are fundamental differences between classical and quantum information, and that tells us what is so quantum about this quantum information. Okay. Classical information we all know. You can copy, you can delete, you can flip, you can do whatever you want to do. But quantum information cannot be, cannot respect all these things. Okay. And also we saw that no deletion and stronger no cloning, they actually link to conservation of information. And classical information is physical but has no permanence. Quantum information is also physical but it has a quality of so-called permanence. To produce a copy, we have to import from some part of the world, and to delete, we have to export it to some other part of the world. And also, I tried to highlight that you cannot design not get, Hadamard get, and C not get. And that implies that quantum computer are inherently personal computer. And this I did not cover, but essentially this is trying to tell that you can erase, but you cannot partially erase. So quantum information, whatever that could be, is actually an indivisible entity. And in no hiding, we try to show that if the original information is missing, it must be moving to some part of the world where it continued to exist. Uh, and in no masking, we try to show that it is impossible for you to keep information only in the correlation. That is arbitrary quantum qubit cannot be masked. So all these impossible operations are fundamental consequence of linearity and unitarity of quantum theory, because these are two basic tenets which the theory has to respect. And any prediction that, as I said in the beginning, any prediction that you do based on these two, better you respect those. Okay. So here is my answer to the question that I raised in the beginning. What is quantum information? Quantum information is something which is inexpressible in classical terms and is unclonable, undeletable, unflippable, indivisible, unhideable, and unmaskable. Okay. So this is my answer. So somebody may find a better answer to this question in future, but this is the thing that we have at the moment. Okay, so with this, I thank you for your attention. So if you have any question, then I will be happy to answer. You mean you need a copy of my slide? Yeah, I can send later on. Yeah, I can send by email. Yeah, yeah. Hmm. Okay, okay, okay. Yeah, I don't know. Hopefully, yeah, it will remain. So let us see. Yeah. So maybe yeah. So this is good. I just realized. I mean, once you said this, so I think next time I will use this microphone. I think this is headphone. This is better. I think something better. Yes. Yeah. Okay. 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 Thanks.
Thank you, sir.
Okay. Thanks. Yeah.